Now that you are familiar with the TensorFlow ecosystem, let us start with the TensorFlow Keras API. TensorFlow provides a high-level TensorFlow Keras API. It provides us three different ways by which we can define our models: the Sequential API, the Functional API, and model subclassing. In this section, we will be learning about these three different programming models. Our goal is to understand how to define models using these APIs, plus also to decide which particular mechanism or technique is better suited for our particular purpose. You can mix and match the three styles as per your needs. So let us start up with the Sequential API. The Sequential API is the most simplest and intuitive. You can think of it as a stack of layers. Here we add layers one by one in a sequential fashion. All the layers which are supported in the TensorFlow.Keras layers can be used as the layers in the model. So for example, we can have the dense layer, we can have the convolutional layer, we can use the recurrent layers, we can have the dropout, batch normalization, and so on. So all the layers which exist which are defined within the TensorFlow.Keras.layers module, they can be used as the layers in the sequential API. Now, how do I start up with the sequential API? So the first thing that we have to do is we start with the sequential class, which is defined in the TensorFlow.Keras.models module. So if I have to start up with the sequential API, the first thing I will do is I will start with my model, and I will define that model as a sequential, as an instance of the sequential model class. Now, after doing that, I will add all the layers of my model one by one as a stack, with just one important thing to remember, that the first layer, that is the input layer, that should have an input shape parameter. Alright. So for example, here you can see I have added the first layer, and here I've defined using the add function. Here I've added a dense layer with 4 neurons and input shape of 100. That is 100 features of the input, and there are 4 hidden neurons. All right. So once you have decided with the layers, you have added the input layer, you can add the rest layers by just using the add method, right? And within the add, you define the layers that you want to use. It can be the dense layers, convolutional layer, dropout layer, or batch normalization layer. So for example, in this slide, you can see that I'm adding a dense layer with 122 neurons, and then another dense layer at the output with 10 neurons. The complete model is given here. So we start up with the sequential. So we create an instance of the sequential class. We start with the first input layer, where we need to define the input shape. You can see that here I've also used name as an option, because that helps when you are seeing the graph of the model which has been created. And we can also add up the activation functions if we want to use different from the default. So we can have ReLU activation function, softmax activation function, leaky ReLU activation function, or even sigmoidal activation function. So here I have defined a model which is basically using the sequential API, and this model has 3 layers. The first input layer contains 4 neurons, then the hidden layer contains 122 neurons, and then the last final output layer contains the 10 neurons. You can see the summary of the model out here. So since the input layer had 4 neurons, and the features that we have defined, the input shape we had defined was 100. So the number of trainable parameters, that is the weights which are connecting the inputs to the input layer, the first dense layer of the network, will have 4 into 100 plus 4, that is 404 training parameters, that is the weights, which are weights and the biases, right? So there are 400 weights plus 4 biases for the 4 neurons. Similarly, if you want to do it for the hidden layer in between, so there will be 4 into 122 plus 122 trainable parameters. So 4 into 122 will be the weights plus 122 will be the biases. And then again for the dense layer, the last final layer, it will be 122 into 10 plus 10, that is 1230 in total trainable parameters. And as a result, I have 2244 trainable parameters. We can also see it as a graph using the TensorFlow Keras utility plot model. So here you can see that it is taking up the input and it is then passing it to the dense layer. That is the first dense layer, then dense layer 2 and then dense layer 3. Alright, so this is the model that we had created. You can also save this model as a file so that you can refer it up later. Now, one important thing when we are defining a model is thinking about weight initializations. For any reproducible result, it is important that weights are initialized properly. There are a lot of options within the TensorFlow API to declare different types of initializations, and we can do the weight initializations using the parameter kernel initializer. So out here I've mentioned three commonly used kernel initializers: the random uniform, which initializes the weights to uniform random small values which lie in the range of 0.05 minus to 0.05 plus. Then we can have random normal initialization. Here the weights are initialized as per a Gaussian distribution with zero mean and a standard deviation of 0.05. Then we can also initialize all the weights to 0 by using the kernel initializer parameter set to zeros. There are again a large number of uh, initializations possible, and you can refer to all the initializations with the full list of the full all initializations using the TensorFlow API documentation. Now, once you have defined your model architecture, the next step that comes is compiling the model. Now, what do I mean by compiling the model? The compiling means we specify the loss function that we want to use. Now, just to I will say revise, the loss function is the function which my algorithm or my model will try to minimize so that it can learn. All right, then we define the metrics. The metrics are the metrics which again the Keras optimizer will monitor as it is training the model. And then there is an optimizer. The optimizer is basically the algorithm which will be calculating the differential so that the loss function is minimized. All right, so again TensorFlow gives you a good option of different types of optimizers, loss functions as well as metrics. So you can have a stochastic gradient optimizer, you can have an RMS drop optimizer, you can have Adam optimizer, you can have Ada delta optimizer. So this is quite big. Again, losses, you can have mean squared error, you can have cosine similarity, you can have sparse categorical loss, and so on. Again, the matrix can be the accuracy, precision, recall, losses, different type of losses that you have defined, even they can be part of your metrics which you can use. Now, once you have defined the model using the sequential subclass, adding the layers using the add function, you have compiled the model, that is specified the optimizer to be used, the last function to be used, and the metrics to monitor. Then the next stage comes training this particular model. So the training of the model is done using the fit method. In the case of the fit method, you just take the model and do model.fit and you pass your training data set. You can specify the batch size, you can specify the number of epochs, and you can also specify if you want to use validation. Now, it is always considered a best practice that we we split our data set into three: the test data set, the training data set, and the validation data set. The training data set is the data set which my model is trained upon. That is this is the data set which my model actually sees. Validation data set is the data set on which I test my model as my model is being trained. So the performance of the model on the training data set and the validation data set, the difference between the performance in two, tells me whether my model is overfit or my model is underfit. In the case my training accuracy or training loss, that is whatever metrics for the training data set is good but not that good for the validation data set, then that is telling me that my model is basically overfitting, and then I need to use techniques to mitigate the overfitting. All right, and then once the model is trained, then test data set is the one on which we test whether the model is really behaving the way it should behave. Again, test data set has the data which the model has never seen before. All right, so this should give us a good idea whether our model will work in the real world, that is, it will work with the data set which it has not seen earlier. Now the fit method, it returns a history object, and this history object records the loss values of the loss values as well as the metric values during the training. And this is again used to make the plots for your losses and accuracies and other metrics that you have defined while training. And these plots are again used to understand the learning behavior of the model. Now, once the model has been trained using FIT, the last step that comes is evaluating the model. So as I said, we can evaluate the model on the test data set. So here you can see we can define use the model.evaluate and pass it the test data set, both the X and the Y, and we can compare whether we are getting a good accuracy or good metrics or minimum loss also or not. And then we can launch the model. The model is ready for deployment, and there you will be using the predict function to get the output for any particular input, any new data. All right, now the question arises, sequential API is, as you can see, very easy to use. The question arises when I cannot use it. So I cannot use it if I have a model which has multiple inputs. So there are more than one inputs or more than one outputs. I cannot use it when any of the layers, not just the input and the output, when any of the layers in between has multiple inputs or outputs. So if you again go back to the sequential API stack structure, you can see that I had only one input per layer and one output per layer, right? But in the case I have in a model architecture where we have a particular layer taking more than one input or giving more than one output, I cannot use a sequential API. Then I cannot use a sequential API if I'm sharing a layer among other layers. So if there is one layer which is being shared between more than one layer, I cannot use a sequential API. So in essence, I can say that we cannot use a sequential API when we have a non-linear topology. I hope the sequential API is clear to you. We'll be using the sequential API to train our models in the second module. All right.